Hi guys. So I will solve the questions starting from this one, 8. Okay, we solved the first 7 questions in the class, so I will continue with this, and then I plan to solve some of the questions from this one too, until this one, 5th question, or maybe 6th, and then we will solve the rest in the next class. All right, so let's start with this question 8. So here we're given functions. We will first find the intervals on which the given function is increasing or decreasing, and then local max and min values of the given function, and then the intervals of concavity, and of course inflection points also. So let's start with this one. F of x is given by this 2x cubed plus 3x squared minus 36x. So to determine the intervals on which the function is increasing or decreasing, we need to first find the critical points. So how do we find them? And these critical points are either the points that make the function undefined, or that make the derivative of the function 0. Okay, so first we need to find the derivative of the given function, which is here. You already know how to take derivative. So we equalize it to 0 to find the critical points. If you simplify that by 6, you will get this equation. Okay, so we can rewrite this as in this form, as the product of x plus 3 times x minus 2. So it gives the roots x equals to 2 and x equals to minus 3. Now these are the critical points of the given function then, all right? What else? As this is a polynomial, there's no point which makes this function undefined. It's always continuous on real numbers, so we don't need to check that again. So we see the derivative of the given function is positive when x is greater than 2. How do we find it? You may either try a point, picking a point from here. For example, let's take 3. So you put here x equals to 3, you plug that, and you get, you observe if it's positive or negative. You can do that. Or you have a polynomial, so you can also do this method, apply this method too. You have 2 roots, right? So, and the sign the multiple of x squared, which is the highest, the x with highest degree. So you see its multiple is positive, so you start with positive. It's only valid for if you have a polynomial, okay? If you don't, you can pick any value from here, from this interval, and try it in here, in the derivative. Again, observe if it's positive or not. So we can plug x equals to 3 here, and we see it's positive. So we have positive plus here, and you can change if you have a root which is odd degree, so each of them is of degree 1, so we can change the sign here. Okay, and then again we change that. So at the end we have this table. Now we see it's positive here, so f prime is positive on this interval -3, from -infinity to -3, union to +infinity. So f is increasing on here and here, and it's decreasing on this interval, which is -3, 2, right? Okay. Now what do? We need to find we can also see from here that it has local maximum here and minimum here, right? Okay, now what about concavity? Okay, we said that already. It has local max at here, x equals to -3, and minimum at x equals to 3. Now, for concavity, we need to find first the second derivative. All right, so we first find, we already found f prime, so we have this. Now, taking the derivative of this function, we get 12x plus 6. Okay, so f double prime is then the second derivative of the function is then equal to this one. Now, equalize it to 0 and find this root, x equals to -1/2. Okay, it's a root of f2 prime. Now, again, we need to check the sign of this f double prime of the second derivative of the given function. So just pick any value from here. It's easier to take 0. So we see if we plug 0 here, we will get 6, which is positive. So we start with positive. And here, for example, you can take -1. So if you plug that, you will get something negative. So we have this. Now, when f2 prime is less than 0, if it's negative, then the graph of the function should look like something like this. So it's concave downward, okay, on this interval now. And it's concave upward when x is greater than -1/2. So, and note that x equals to -1/2 is inflection point. We say a point is an inflection point if the graph of the given function is changing from concave upward to downward or concave downward to upward, okay? When it changes its concavity, so we say that point is an inflection point, okay? So we're done. Now, what about this? Part D. We're given sinus x plus cosinus x on this domain. So we have this restriction, okay? Now, first take the derivative. We have cosinus x minus sinus x and equalize it to 0 to find the critical points. Thus, it gives that sinus x equals to cosinus x. So when we have this equality, when it's pi over 2, let's this unit circle. So it's either, in other words, when do we have this, right? You may ask to yourself to this one too. So either it's pi over 4 or this part, right? So it's pi over pi plus pi over 4, which gives pi over 4, which is in here also. So they are both in the domain, so they are the critical points. Okay, now we say just pick any point from here to determine if f prime is positive or negative. For example, if you let's do that on this table too, unit circle. All right, now when we're in between 0 and pi over 4, what do we have here? This is pi over 4, right? We have cosinus x minus sinus x, right? We have cosinus x minus sinus x. So here between 0 and pi over 4, we need to just check if f prime is positive or negative. So here between this from 0 to pi over 4, cosinus is greater than sinus x. So it gives this f prime is positive. When it's in between here, this is also pi over 4. When it's in between pi over 4 here and 5 pi over 4, what do we get? For example, we can take any point from here. Let's take pi over 2, for example. Cosinus pi over 2 is 0 and sinus pi over 2 is 1. So we get -1 here, right? So it's negative. And for that part, we can, for example, take this one, which is 3 pi over 2. So it will give us something positive. If you can try it, you will get. So we will get something positive. So it gives f is increasing here and decreasing on this interval. So in other words, f is increasing on 0 pi over 4 union 5 pi over 4 2 pi, and it's decreasing on pi over 4 5 pi over 4. Okay, so it has local max at the point pi over 4 and local min at 5 pi over 4. Okay, and what are the local min and max values of this function? We need to just plug them. Okay, so for example, for this one, you will have sinus pi over 4 plus cosinus pi over 4. So you will get square root of 2 over 2 plus square root of 2 over 2. You will get square root of 2. And you can plug that to find the local minimum value of the function. Okay, that part is easy. Now for the last parts, what do? We need to determine the concavity of the given function. So for that, we need to find f2 prime. Remember, f prime is this. So we take the derivative of this function, which is this one's derivative is minus sinus x, and this one cosine x. So we have this, right? It gives cosine x is equal to minus sinus x, which gives again sinus x over cosine x is equal to -1. So tangent of x is equal to -1. Then do we have that again, unit circle. So we know here on pi over 4, here we have 1. So we need to have here, if we have -1, then the values of sinus and cosine should be equal to each other, but with the opposite signs, right? So either we are on here, we have pi over 4 there, which gives you can either find like this, or you can write it pi minus pi over 4, right? They are the same. And so here 3 pi over 4 is this part, and they have opposite signs here, again pi over 4. So you can find it like either 2 pi minus pi over 4, or with this, so 3 pi over 2, 3 pi over 2 is here, plus pi over 4, you will get this. All right, so we have these two points. These are the roots of f2 prime, right? Now, again, by picking a point, you determine the sign of the function, f double prime. Okay, so when we have negative, it's concave downward. Then we have positive, it's upward, negative, downward. Okay, what are the inflection points? They are x equals to 3 pi over 4 and x equals to 7 pi over 4, right? Because it changed its concavity there at those points. All right. So we're done with this question 8. We will solve 11 and 12. So we will find the minimum vertical distance between these two parabolas. Okay. So first, write a function in terms of only one variable, x, okay, which gives us the distance between these two parabolas. Okay. So we write it as in this form, x squared plus 1 minus x minus x squared. As this function is greater than, has values greater than this parabola, we write that one first, because as we write a distance function, it should be something positive. It should give values positive or 0, right? That's why we first write this function. Now, what do we do here? We need to find minimum vertical distance. That's why we need to minimize this function b. Okay, so how can we do that? We need to first find its derivative and equalize it to 0 to find the critical point. Okay, so let's do that. So this one's derivative is here. So if it's equal to 0, I'm sorry, here we have the derivative. If it's equal to 0, we have x equals to 1/4. Okay, by the first derivative test, or you may again find a table like this. Okay, if you make this table, you can pick any point, for example 1, and you plug here, you will get something positive. So we start with positive, plus, then negative we have. So it's decreasing, then increasing. So this is local minimum for this function d, which means that if you plug x equals to 1/4 into your function, you will get the minimum point of that, minimum value of that function. Okay, so we just do that to find the minimum distance between these two parabolas. Okay. Now we will find dimensions of a rectangle, okay, whose area is this, okay, so that its perimeter is as small as possible. Okay, so we want its perimeter to be small, okay, and we want its area to be this value. Okay, so first write its perimeter. So if we call this dimension x and this one y, so we have its perimeter is 2x plus 2y. We want this perimeter, this function, to be minimum. Okay, so it means we need to minimize this function, but it's a function with 2 variables. We don't know that yet. So we need to write one of the variable in terms of the other to get a function in terms of one variable, a function with one variable. Okay, so how can we do that? We will use this info here. So its area is this, so it means in terms of x and y, we get xy equals to this 1,000. Okay, so here I choose to write p in terms of only x, but you can do that by changing these variables. So without loss of generality, we have y equals to 1,000/x. Now we rewrite this function p by plugging this equality here. We get this function. Okay, so now we have a function in terms of only one variable. Now we can minimize it. So how can we do that? We first find its derivative and equalize it to 0. So it gives x equals to this one. X cannot be negative here. It's a dimension. So we pick the positive value of that variable. All right. So by, again, the first derivative test, we know this gives the local minimum of p of x, right? So we just plug that point to oh, we don't care about it, sorry. We only find the dimensions. So x, one of the dimensions is this then, and the other one is y. We have this equality, so we get this variable. Okay. All right, 15. Now we will find the point on this curve, y equals to square root of x, which is the closest point to this point, which is 3, 0. Okay, so for that, we need to first write a function which gives us the distance between 2 points on R squared, right, on the coordinate system. So, for example, if we have this point x comma y, we don't know that point yet, so let's call it x comma y. Okay, so and we need to suppose that it's on the curve, right? It's not important for now, but for the second one, it will be important. So suppose that x comma y is on the curve. Okay, so the distance of this point to this one, 3 comma 0, is this. So we take the difference of the first components, which are x and 3, which gives x minus 3, and then their square, plus the second components, the difference of the second components, and square, and then square root of them. Okay, this is the distance function of 2 points on R squared, on the coordinate system. Okay, so if we rewrite it, we get this one. So you see, again, we have a function in terms of with two variables, a function with two variables, x and y. So we need to write one of them in terms of the other to find a function, to obtain a function in terms of only one variable. So we know that point x comma y is on the curve, so it should satisfy this equality. So we have y equals to square root of x. Now just plug here y equals to square root of x, so we get this now. Okay. So what do we do here? We need to find the closest such point, so we need to minimize it. So it means, now you know it, d prime, so find d prime, then equalize it to 0, then find that root, which is 5/2. So x equals to 5, at that point, x equals to 5/2, d has the local minimum, okay? So if we plug, what do we do here? We need to find that point, right? So we have already first component of that point, which is 5/2. We know that point satisfies this this equality, so we just plug that to find the second component of that point. So this is the closest point on this curve to this point. Okay. All right. So we have a poster now with some margins 6 centimeter and 4 centimeter, as you see in here in this picture. We have such posters. Okay. Now the area of printed material on this poster, which is this one, okay, the inside rectangle, is this. Okay, so the area is this. We know that. What do we do here? We need to find dimensions of this poster. Okay, what are the dimensions now? So here we had y, right? 4 plus 4. So we have here y plus 8. And here we have x plus 6 plus 6, x plus 12, all right? Now, first, we need to use this info here. So the printed area is here. So its area is x times y. Sorry. Oh, the printed area is the whole area. Okay, sorry. Okay, this whole thing is the printed poster, right? It's so its area is y plus 8 times x plus 12. Okay. So we have this function again with two variables. No, I'm making a mistake here. Yes, I was right before. So this was, yes, this is the printed material. This is the printed area, sorry. So xy is equal to this now, right? We need to okay, we want that pastor, the dimensions of the pastor, to be small, right? So we need to minimize it again. What do we have as function? We have a, so we have x plus 12 times y plus 8. Okay, so we need to minimize it. And we have this info again, so you know that already. So we need to write one of them in terms of the other. So what do we have? We have from this equality, we get y equals to this x. Okay, so we plug here instead of y, we write this. Okay, and it gives this function. Now we have a function in with one variable, only one variable, right? Now, how do we minimize it? We take the derivative of this function and equalize it to 0. So x is either plus 24 or negative minus 24, but it cannot be negative as it's a dimension. So we have this, x equals to 24. Now, we need to find y also. Here we had before this equality. So if we divide this number by 24, we will get y, the value of y. Okay. Now, what are the dimensions? X plus 12 gives x equals to 24. Just plug that here. We have one of the dimensions is this, and if we plug y equals to 16, we get that. All right, so the printed area, I was right at the beginning. So the printed area was x times y. Okay, it's given here. And we write this this whole area as a function of x and y. Okay, so to minimize this function is the same with minimizing the dimensions of the pastor. So that's why we use this function again. Okay. All right. Now the last question of this worksheet. All right. Now start with the first one. Okay, I'm gonna write here the answer. So we will find the demand function. And here we assume it's linear. It means the degree of x is equal to 1. Okay, not a curve, a linear function. Okay. So this is a linear function. All right, and now first let's p of x to be y. This is the desired function, the demand function. So what do we know here? We know this is equal to 10. So if the ticket price is this $10, then the attendance is here, right? So when it's $10, we have this many people. What else do we know? When it's $8, we have this many people, so we have also this. All right. We know this P should be linear, right? Now we need to find its slope, right? We will, at the end, eventually, we will write a function, a line equation, right? How can we write a line equation? What do we know? What should we know to write an equation of a line? We need to know its slope here, which is a, okay, and a point on that function. We already know the point on it. For example, this is one of the points on that function p, or we may use this one too. But we need to find its slope. How can we find this? We know 2 points on it, right? The other one is this. So we will use that. Its slope is, if we have 2 points on it, it's given by this one. So what do we have? We have 10 minus 8 over, 27,000 minus this, okay, which gives us here this one. Okay, so what do we have now? We have P of X is equal to minus 1 over 300, sorry, 3000 X plus some constant. Okay, we found that A. We need to find that constant now. Okay, how can we find it? We can pick any, we can plug any point on it to find that C. Now, if we plug, for example, this point, we just plug here, instead of X, we write this point and equalize it to 10, right? So what do we have? C is 19 then. Therefore, P of X is this function now. So let me just write here. It's 19. Okay. Now, what about the second part? So now we need to maximize. Okay. Now we have another function, R of X, which gives this. So it is X times P of X. Okay, the number of the people times the price. Right? So what we have now, we just multiply this function by X. So what we have, minus X squared over this plus 19X. All right. All right, now what do? We need to maximize it. So we first find the derivative, R prime of X, okay, which is this minus X over, and equalize it to 0 to find the root, which gives X equals to this one, okay. So by the first derivative test again, we see that R of X has local maximum, right? You can make a table to see clearly that part. At that point, at X equals to this, okay. Now, how should the ticket price be set? It asks. So we need to find P of X at that point. Thus, P of this is equal to 9.5. This should be the ticket price. Okay. All right. So we first write that function, revenue function, okay, as in this form, because it's the number of the people times the price, right? It gives us this one, revenue, right? So we have this function. We need to maximize it. So we first find its derivative and then the root of that, okay? So this says that if this many people, comes to the stadium, right, we will get the revenue at max. Okay, we will get maximum revenue. Okay, so we need to find ticket price. So if we have this many people, we already know the price function. So if we have this many people, just plug in here, this one, we get the price for ticket. Okay, so we're done. And so we're done with this worksheet. Let's start to 6. All right. Now we have this function. Its graph is given now. Okay. Now what do we do here? We will find intervals of positivity and negativity for f prime. So we know already that if f prime is greater than 0, the function is increasing. And if it's less than 0, the function is decreasing, right? So we already have the graph. So using this info, we can determine if on which interval f prime is decreasing or increasing, okay? So you see the function is increasing. Let's note here. Or that's right, f of x is increasing on here. What? It's increasing on this interval 0, 2. Then you see it's decreasing, right? Then again, after starting from 4, it's again increasing till 6, right? So f prime is greater than 0 on, let's write here. So f prime is greater than 0 on this interval. Okay. What about negativity? We see it's decreasing on here on 2, 4 union here after 6, right? So on here, f prime of x is less than 0. Okay, so we're done with this. Now, what about f double prime? We know that f double prime is greater than 0 if the graph of the function is concave upward, and it's negative or less than 0 if it's downward, right? So we need to determine that. Right, so we see that, let me erase it. So we see that it's downward till here. So you can determine that by taking the tangent lines, right? If it's downward if it's below the tangent lines, then it's concave downward, we say. Okay. So till here, you see it's below the tangent lines. So f of x, let's write it first, concave downward on, so from 0 to 2, we know yet. Okay, then it's upward, we see it's above the tangent lines, right? Then it's again downward. After 6, it's downward, so union 6, 8. So f double prime of x is less than 0 on this interval. Okay, and f of x is concave upward on here, as we said before, from 2 to 6. So f double prime, the second derivative of x, of f, is greater than 0 on this interval. All right. As we said before, it's increasing on here and decreasing on this interval, right? And we already checked the concavity for intervals here. What about the points of local minimum and maximum of f? So here we can make the table first. Maybe it will be clear. F of x, f prime, f double prime. So what do we have here? The points 0, 2, 4, 6, and 8. Okay, the domain is here from 0 to 6. So what did we say? We said f prime is positive on here, on 0, 2, 4, 6, and they're negative. And f 2 prime is less than 0 on here and here and there upwards, right? So it's downward here, upward, upward, and downward. And it's increasing, let me write here, increasing, decreasing, increasing, and then decreasing. So its local max is here, x equals to 2, local minimum at x equals to 4, and local maximum at x equals to 6. And the inflection points are x equals to 2 and x equals to 6, right? Here it doesn't change its concavity at the point 4, so it's not an inflection point, but 2 and 6 are. Okay. All right. So what about this? Now, what's the domain of the function? We're given this function, f of x is x squared minus 1 over x squared minus 4. So the domain is, domain contains the point in real numbers on which the function is defined, right? This function is not defined when the denominator is 0. So if x squared minus 4 is equal to 0, which means x equals to plus minus 2, and so these points make the denominator 0, which means these points make the function undefined, right? So these 2 points cannot be included in the domain of the function. So it's R except these 2 points. Okay. So what about this? Let's compute that together. Let me write here. So we have this function. Third question, f of x is given by this. It's x squared minus 1 over x squared minus 4. Okay, so we already found the domain. Now observe that f of minus x is equal to here minus x squared minus 1 over minus x squared minus 4, which gives x squared minus 1 over x squared minus 4, which is f of x already. So this says f of x is even, okay, and so its graph is symmetric with respect to y-axis. For example, for example, x squared, the parabola, this function is also even. Minus x squared is equal to x squared, so this is even, and it's symmetric to y-axis. The same with this function too. Okay, it's even and it's symmetric to y-axis. All right, so this is the one of the blanks in the second part, and the other one symmetric with respect to y-axis. Okay, and for the other part, let's check that together. Here, y-intercept is the point where x equals to 0. Okay, so we just plug x equals to 0 here. We will get 1/4. So y-intercept is 1/4. So it means the graph of the function cuts the y-axis at this point, 1/4. And x-intercept, so it means y is equal to 0. So we equalize it to 0. X squared minus 1/x squared minus 4 equals to 0. Then it gives x equals to minus plus 1, right? So these are the x-intercepts, plus 1 and minus 1, okay? And what about the limits of the function? So compute here together. On the whiteboard again. So limit of f of x when x is approaching infinity. What do we have here? We write this function in the parentheses of the numerator in the parentheses of x squared, which gives 1 minus 1/x squared, and the same for this one too. Okay, so we can simplify them. Now, when x is approaching infinity, we have zeros here, so we get 1 as limit. And similarly, limit of f when x is approaching minus infinity will give us again 1. Okay. Hence, this gives y equals to 1. This is the blank for that part, is the horizontal asymptote. Okay. Right. So, okay, we found that these are 1s. So y equals to 1 is the horizontal asymptote. What are the vertical asymptotes of the function? Now, for that, we know the function is undefined when x is equal to minus or plus 2, right? So for vertical asymptotes, we need to check the limits at those points. Okay, so let's do that on the whiteboard again. So for vertical asymptotes, what do we have? We have this limit. So we have x equals to minus plus 2, right? The points which make the denominator 0. So for those points, we need to check the limits. So let's start with 2 plus. So f of x is this, x squared minus 1, x squared minus 4. So when we're approaching 2 from right, we have something greater than 4, right? As we have here x squared. So we will have eventually here in the denominator, we will have 0, but we have something positive, and the numerator is also positive. So it gives plus infinity. And similarly, you can find the limit of this function at there too, minus 2 from left, okay? And limit of this function f of x, when we're approaching minus 2 from right, will be equal to minus infinity. Okay, we already know them. We don't need to write it again and again. Okay, So we have these values now. It means these 2 points are from left and right. They are vertical asymptotes. Okay. This one was the horizontal asymptote, and this one was the vertical asymptote. These one. Sorry. Okay. Now, okay, what's the derivative of this function? We will find that. And the critical points. Okay. And then we will determine on which intervals f is increasing or decreasing. Then for concavity, we will examine that too. And then we will sketch the graph of the function. Okay, so I'm not going to return here. So let's do them on the whiteboard. All right. So let's find the derivative first. F prime of x. So the first one's derivative times the second one, we will apply the quotient rule, x squared minus 1, and the second one's derivative over this, x squared minus 4 squared. Okay, if you simplify these things, you will get minus 6x over x squared minus 4 squared. Okay, so we equalize to 0 to find the critical points, which gives x equals to 0. But here remark that x cannot be equal to minus 2 or 2, right? They are not in the domain. What do we have here now? Let me write there. So let's do the table here. Okay, now we have f prime, f double prime. Right, so minus 2, 0 is the critical point, and 2. Okay, these are the not roots of f prime, but they are important. They will be important. So all right, now we have this root x equals to 0 for f prime. So when x is greater than 0, you see that when x is greater than 0, this will be negative. The denominator is always positive, so we will have something negative here. So when x is greater than 0, we have the values of f prime are negative. And similarly, you can see that when x is less than 0, the values of f prime are positive. Okay, so it means f is increasing here and decreasing on these intervals. Okay, now what about the concavity? So we need to find f2 prime now, right? What's f2 prime? Just take this one's derivative. Okay, you will get 18x squared plus 24 over x squared minus 4 cubed. So equalize it to 0 to find the roots, but we see that has no solution, has no root here, right? And because x is a real number, so 18x squared cannot be equal to minus 24. It means f double prime has no solution on real numbers. But remark that when let's check here. Okay, when x is greater than 2, we have something positive here. right? The numerator is always positive, so let's check only here denominator. When x is greater than 2, it's positive, so we have plus. Okay. Now, when x is in between 0 and 2, for example, pick any value from here. For example, take 1. If you take 1, you will get something negative. As we have 2 here, we will get negative in the denominator. As this is positive, we will have something negative. So on this interval, it's negative. And again, take -1, you will get the same result, so it will be negative. And then by picking, for example, -3, you will get something positive. Okay, so between -2 and 2, f2 prime is negative, and otherwise it's positive. So it means it's upward, downward, downward, and upward. Okay, the graph will be like this. Okay. Now, using these informations, we will try to sketch the graph of this function. So let's do that. So recall that y equals to 1 is horizontal asymptote, and x equals to -+2 are vertical asymptotes. Okay, and this is y-intercept, and these are x-intercepts. Okay, and also this is important. So limits of the function when we're approaching 2 from right is infinity plus infinity. The same for the point -2 from left, and these are -infinity. Okay, so we will use these informations to sketch the graph of this function. So let's write the coordinate system first. So here we have y equals to 1, which is the horizontal asymptote, right? So first write it like this, sketch it like this. Okay. Then what else? This one too, x equals to, call this 1 and 2. So this is also horizontal vertical asymptote, and -1, -2. So this is also vertical asymptote, right? Now, what else do we know? We know the y-intercept, right? So 1/4. So this is on the curve. We know that. And these are also on the curve, on the graph. So we will have these points. Okay. Now we will use these informations to sketch the graph. First, look at here. When x is less than -2, we see the function is increasing. Okay. So the function should be increasing. It's on that interval, it's upward, it's increasing and upward, so it should look like this. Okay. Now it should look like that, and we know that y equals to 1 and x equals to -2 are asymptotes, so the graph cannot cut these lines. But here, if we sketch it like this, it will look like this, right? It will look like this. So, but this is up, downward, right? It's downward. It cannot be a part of the graph. So it will look like this. Also, you can use these infos. For example, when we're approaching -2 from left, -2 from left, it's approaching infinity. So here, as you see, it's infinity. And if we're approaching, oh, I forgot to write that. So the limit of the function when we're approaching, infinity, minus infinity, and infinity, they were both 1. Remember that? So here, we're approaching minus infinity. X is approaching minus infinity. So this the graph is approaching 1, right? So it's okay now. Let's look at here too. It will be easy again. It's decreasing when x is greater than 2. It's decreasing and upwards. So it should look like this. Okay. And what about here? And when x is approaching infinity, it's 1. It can be either from this or this. It doesn't give info here. So what about here? We're approaching 2 from right. 2 from right. So we have plus infinity. So we should have something like this. Okay. Now, what about this? So the graph of the function should cut these 2 points, right? So it should look like this. It gives directly the graph, but let's examine here. Okay, check this part. So we're approaching -2 from right. It should be -2 from right. It should minus infinity. It's correct. And 2 from left, it's again minus infinity, as in here. Okay, and it cuts these 3 points, right? What about here? It's concave downwards. It's increasing till 0. It's increasing till 0 and then decreasing. So it's also correct. Okay. So you should first, to sketch a graph of a function, you should first find the domain of the function, then y-intercept and x-intercepts, okay, as we did here and here, okay. Then asymptotes, vertical and horizontal asymptotes. Then for that, vertical and horizontal asymptotes. And then the critical points, it means f prime, then equalize it to 0 and find the critical points. And then sign of the of f prime, okay, on the intervals. Then determine if f, on which intervals the given function is increasing and decreasing. And then find f2 prime, equalize it to 0. Then find the inflection points, right? And the sign of the, before you need to do that, first you find the sign of f2 prime. Then you determine if the function f is concave upward or downward, okay? So you will eventually find the inflection points, all right? Then you can start to sketch the graph, okay? All right, so we solved this third one too. Right, fourth. This one. So we will do the same things here. I guess in this, at the end of this question, it will be clearer, more clear. So we're given here this function. We will first find the steps that I counted before. Okay, then sketch the graph. So first we find f prime. Okay, we are given this function. We find f prime, equalize it to 0, and then find the roots of this function. Okay, So they are x equals to 0 and x equals to -2. Okay, we have these two roots now. It's a polynomial, so we have the domain is real numbers. Okay, we have no restriction. So, for example, for picking here from this integral 1 and plug it here, you see it's positive. So we start with plus, then negative, then positive. So f is increasing here, decreasing, and then increasing. Okay, so it has local max and minimum here. Okay, so let's all right. Right. Then what about here, f2 prime? We need to determine the concavity of the function f also. So that's why we need to find f2 prime here. So take the derivative of this function and equalize it to 0. Find the root, x equals to -1. Okay. Now, what do we have? We have just pick any point from here. For example, 0. If you plug 0 here, you will get something positive. So we start with plus, then negative. So it's downward and then upward. Okay, it was increasing, decreasing, and increasing. And here we have first downward, then upward. Okay. Now, we need to sketch the graph of the function. So first, let's rewrite the function f of x. Or maybe, okay. All right. Now what do we have? We know that f is increasing on here -infinity, from -infinity to -2, and on this interval 2. And let's do the table here. What are the points? We have -2, -1, and 0. -2, -1, and 0. Okay, f prime, f double prime, and f. Okay, so these were the roots of f prime, and this was the root of f double prime. So we see on here plus, negative, then plus, and here we have plus, negative, negative. All right. So what do we have? So let's note it here. It's increasing, downward, decreasing, decreasing, increasing, downward, upward, upward. Okay. All right, so here you see it's increasing and downward, so it should look like this. Okay, from -infinity to -2, it should look like this. We just plug x equals to 0, you see the y-intercept is -1. Okay. So what do we have here? We didn't find the it doesn't matter. So let's determine them too. We have something decreasing and downward, so it should look like this. Okay, and here it's decreasing and upward, so it will look like this and like this, increasing and upward. Okay, so at the end, what will we have? We will have something like this. So here you see this is the inflection point, and sorry, it's not the inflection point. This one is the inflection point, and that's it, right? We have only one inflection point. We have here local max and local min. So it should look like this. Sorry, guys, it will be easier to sketch here, so I note them, note the table here. Okay, so here we have the function. We already found the table. We know f of 0 is equal to -1, so we have this point. This should be on the graph. And we know the inflection point is here, -1, and this is the local max, and this is the local minimum. All right, so what do we have here? We will sketch approximately, right? We don't have vertical asymptote, horizontal asymptote, something like this. So we will sketch that approximately. It's not as in the previous question. So, but we know that here in the, at this point, -1, we need to have a change, we need to change the concavity. Okay, so until here, until -2, we have something like this. Okay, then it should be like this, right? And what else? So now in this point at x equals to -1, we need to have something like this, right? So it should change its concavity from downward to upward. So something like this, but we know it cuts here. It's a y-intercept, so we need to have something like this there. For example, something like this. It's from downward, it changed to upward. And then it should cut this point and then goes like this because it's increasing and increasing and upward. You see, after 0, it's increasing and upward, right? So at that point, -1, this is, as I said before, this is approximately. At -1, its graph changed its concavity from downward to upward. Okay, it's an inflection point. It cuts this point. All right, everything seems okay now. Yeah. Okay. So I will solve this one on the whiteboard again. It will be more clear on there. Okay, so the function is f of x is equal to x minus sinus x, and we're given the domain already. X is in between 0 and 4 pi. Okay, so the question asks only, let's look at the question. here we're in this part. We will find only the intervals on which the function is increasing and decreasing, and local maximum and minimum points, and the concavity inflection points, and we will sketch the graph, okay? No vertical asymptote or horizontal asymptote, okay? All right, now first, what do we have? We find f prime of x, which is 1 minus cosine x, and equalize it to 0. Then what do we have? It gives cosinus x is equal to 1 on this interval. Then on which points cosinus is 1? On 0, 2 pi, and 4 pi, right? The even multiples of pi. Okay, so these are the critical points then, right? And so let's make the table here, f prime. So we have 0, let's note them too. 2 pi, 3 pi, and 4 pi. Okay, we will find f2 prime also for concavity. Okay, so for example, let's start with this one. We can pick pi over 2 here from this part, this interval. If you plug pi over 2, you will get 0 there, right? So you will get 1, which gives plus. Okay, and we have, so this is not the root of f prime, so we don't need to check again and again. We can write here. And what about this? If you pick, for example, 3 pi, cosinus 3 pi is minus 1, so you will get something positive there. So it's again positive. Okay, it's always positive. It means the function f is increasing on this interval. It's always increasing. Okay, now f2 prime of x. So what do we have? We take the derivative of this function. We have sinus x and equalize it to 0. So what are the x's here? It's 0, pi, 2 pi, 3 pi, and 4 pi, right? Okay, so all of them are the roots of this function. Okay, we don't care the rest of the this part, the points greater than 4 pi, because we have this restriction. Okay, and is it positive or negative on these intervals? For example, between 0 and pi, it's positive, then negative, then positive, then negative. Okay, so it says it's upward, downward, upward, and downward. All right. Now we need to sketch that, but first note that f of 0 is equal to 0, and f of pi is here. We plug pi here. We have pi minus sinus pi, which gives pi, and f of 2 pi is equal to 2 pi. F of 3 pi is equal to 3 pi. And f of 4 pi, which is included in the domain, it's 4 pi. Okay. Now we can sketch the graph. Okay, so we have 0, pi, 2 pi, 3 pi, and 4 pi. We know this point should be on the graph. And also this one, 2 pi, 3, and 4 pi. This and this. Okay. Now we need to determine if it's concave downward or upward. Now it's upward and increasing, so it should look like this till pi, from 0 to pi. This is on the graph also because we have this. So it should look like this. Okay. Now it's downward. This is an inflection point. So it's downward and still increasing. So it looks like this. So we have this. And as you can guess, it's upward and increasing. So it's like this. And again, this. Okay. This and this should look like the same. Okay. It's my mistake. Okay. So this is the graph of this function. All right. So let's stop here. I will start with this question, fifth, and solve the rest of the questions in the next class. If you have any question, you can visit me on Friday, or you can ask at the beginning of the next class. Okay, hope you understand. All right, if you don't, you will solve this question in the class, so you will get there, I guess. All right.